Still you need this. I understand. Yeah. I see. Yeah. Okay, so we're done. That's 2.5, almost 3 hours.
Yeah.
6 hours travel.
Yeah.
For a very quick visit. Yeah.
Yeah.
Well, it's a small country. Huh? Yeah. Okay, welcome everybody. Looks like, well, at least most of you found this lecture room at this time. Well, we're not fully complete, but to compensate for that, we have a guest today. Really a pleasure to have you here. Actually, I don't know your name, but that's not relevant, I think. You're a bachelor student in mathematics, and you're considering to continue your studies in our program. So I'm calling for your help in convincing her during the break and maybe after the lecture that it's actually a very good idea. Yeah? Okay. So today we're going to continue where we left, so you might miss something, but Rob will be there to help you. That's your work. Yeah, okay. Actually, before we start, one more remark on the composition of the groups. I checked the list and it's almost complete, and as far as I can see, everybody who is here is indeed already on that list. I did notice that despite my urgent advice, we do have a separate group of our foreign guest students. I'm not happy with that, but if you are, there's nothing I can do. I just thought that let me mention it again. Okay, so, meaning that there's still room to change, if you like. Yeah.
When is the deadline?
The deadline for the group composition?
No, for the assignment.
We'll discuss that tomorrow, because I need your input on that. Yeah. Hi. Tim, as far as I observe, you're not yet on a group? No, right, so take care of that today. Yeah? Take a seat. Okay, so indeed, let's see where we are, where we have arrived, talking about the contents of this course. Last time, as a couple of lectures before, we've been discussing recourse models. One of our ways of coping with an optimization problem, in particular linear program, having uncertainty in the constraints. And the idea is then that we have this expected value function Q, which is modeling the expected cost that we need for compensating for any feasibilities that arise as soon as we've decided on our decisions. What we discussed last time was properties, in fact also the time before, last time mostly on subdifferentiability of that function. And of course we do that because we like to study that kind of questions, that kind of issues, but also, and that we will discuss extensively later, because it is very relevant for algorithms, our recipes for solving these models, because in the end, and I've mentioned that before, it's all very nice to be able to specify models, but if you can't solve them, you've got a problem. Yeah, so that's to be continued on that aspect. But that's not the only thing we did last time. We also discussed some easy bounds for the optimal value of that two-stage recourse problem. And we argued, well, despite our knowledge of the properties and our analysis, that doesn't take away that those problems are extremely difficult to solve in general. So the idea is, why not try to solve an approximation, which then should be a lot easier, and if that gives satisfactory answers, we're happy. That's the background. What we're going to do today is continue a bit more on that track, and in fact I'll also introduce yet another approximating model, and we discuss what that contributes to our analysis. Moreover, and that's a second subject, but it is related, we'll be talking about, well, one of the causes for the difficulties, namely that the distribution typically is a higher dimensional distribution, and in particular if the distribution is continuous, then evaluating the expectation, as we need to do many, many times, is a big hurdle, big problem. And therefore it would be of interest to come up with simplifying approximate distributions. So that's what I mean by SLP approximation of distributions. And actually it's for good reason that that's in this lecture, because as you will see, it's closely related to the other things that we discussed last time and today. Yeah, so that's the outline, and let me summarize what we did last time. So our true problem, so to speak, is the two-stage recourse problem defined over there using the convenient notation I introduced last time. Indeed, I'm using this function depending, function g, depending on our decisions x and on the random parameters in our problem omega, which is the objective. And in our two-stage problem, what we're interested in is the expected cost coming from that objective function g. And we try to find the best solution, that is, we're optimizing over a given, deterministically given feasible set, typically non-activities and some linear constraints. And our function g actually consists of two terms, the immediate cost, or first stage cost as we call them, c times x, plus that value function of the second stage problem, which models the cost associated with infeasibilities, which are indeed depending on our decisions and on the actual value of the parameter omega. All right. We do realize that solving this problem is very hard, and that's why we said, why not make it a lot easier? And one way of doing that is to say, well, let's look at what we call the expected value problem. Namely, instead of, well, it's over here. Instead of minimizing the expectation of G, we said it would be a lot easier if we could address instead G of the expectation, where the vector mu is the vector of expectations of a component-wise of our random variable omega, the vector omega. So the expected value problem is this one, also in terms of the same feasible set, nothing changed, but a different objective. And it's very easy to see, knowing what that value function v actually stands for, that what we're looking at is just a linear program. And indeed, that's a lot easier to solve than the full-fledged two-stage recourse problem, which is non-linear. All right. Indeed, we replace the matrix T, depending on that random vector, by its expectation, and the same for the right-hand side. Hence, our goal constraints end up as simple linear deterministic constraints. So that's all very fine. And in our studies, we found that actually, indeed, that simple problem is an approximation, and we know, under suitable assumptions, that it provides a lower bound for the true objective value. In particular, those assumptions are that the randomness is only in that matrix T and that right-hand side vector H. In particular, the cost factor Q is deterministic. So we call that the Groninger version of fixed recourse, remember? And the matrix is of course, I would say, assumed to be deterministic. All right, so that's how we get a lower bound. We argued that to obtain an upper bound is really trivial. Just pick any feasible solution, evaluate the corresponding cost, and that's an upper bound because it's feasible and not necessarily optimal. And then we said, well, actually, to come up with a feasible solution, why do some extra effort if we already know one, namely the solution of the expected value problem? And that I typically denote, and I think it's somewhere over there, yeah, by XEV, the solution of the expected value problem. And this then, the expected result of the EV solution, provides an upper bound. And it's defined, indeed, as the expectation of the function g evaluated in this particular solution. And you might say, well, that's still difficult, because that expectation is with respect to a higher dimensional random vector. But the thing is, of course, that we need to evaluate it only once. So we can afford to spend some time and effort, for instance, by an extensive simulation. In fact, if you look at the software that you will be using later on for the case studies, this is a facility inside. You can just press that button for any given solution, and in not too much time you will get your answer in terms of what is the corresponding objective value. But still, it takes some time, and the issue is that if you have to do that many, many times inside the algorithm, that's not feasible. But here it is, because it's just a single time. Okay, this is what we found, and obviously that is always an upper bound, not depending on any assumptions. Even if we would have random recourse, random cost, it would still be an upper bound, because we're talking about a feasible solution. Okay? So, given that we now have an upper bound and a lower bound, we could look at the difference, at the gap. And the reasoning could be, okay, if that gap is sufficiently small, we're really happy with the solution that we found by solving this simple problem. XDV would then be a very good solution, maybe not quite optimal, but very good, to the advanced two-stage recourse problem. Because that's what the upper and lower bound together then tell us. Because the true optimal value is in between, and if the gap is small, it cannot be very different. So that's one reason to be interested in such bounds, because they might tell us that despite our careful modeling, it turns out that actually the solution is not very sensitive to this uncertainty. That doesn't mean, of course, that we wasted our time in modeling the problem carefully. Right? That's something that we learn from our exercises. Okay, typically that will not be the conclusion. Most problems are indeed sensitive to the uncertainty, so the gap will be too large to say, okay, we can stop here. But still, the information is relevant, and talking about the difference tells us something about the problem. So, for instance, to answer the question, okay, what do I mean if I say the gap is small? I mean, I could just call out any number, and that, without any proper background, that doesn't give you any information. So, in the context of the problem, in the particular application, you of course also always need to consider what the numbers actually mean, and this is one example. If you observe the gap, which you can always calculate, then to discuss it, look to the context and at least consider it in absolute terms. Maybe your application is on some big industrial problem and you're talking about millions of euros in absolute sense. Well, that would be an argument. But then again, if it's relatively speaking only a tenth of a percent point or so, then maybe you hesitate to call that large. Yeah, so that kind of perspectives are relevant. Okay, what we're going to do next is continue our discussion on bounds, and here's the idea. So far, we've been doing the following. Under our standard assumptions, we assume that the recourse is fixed, in particular the costs are fixed, and we assume, of course, that the recourse structure is sufficiently expensive and complete, because that guarantees that the value function is finite valued, and if on top of that the distribution is also nice, in terms of the first absolute moment, that should be finite, which is hardly an assumption. And actually the recourse function Q itself will be finite valued, and we like that for our analysis. Okay, so what is it that we did so far? Well, we looked at two versions of the problem. The two-stage problem, nicely summarized by in terms of the function g, and this is the corresponding picture. It's the timeline, time running from left to right. We are here right now. We need to decide on our decision vector x before we learn about the actual realization of omega. But having probabilistic information, we know the distribution, and then later we are allowed to compensate for any infeasibilities that we observe, but they come at a cost. That's the idea of the recourse model. Then again, we also might consider the deterministic version, the expected value problem, where there is no uncertainty. Actually, sometime later, some information will appear, but we already know what it is, namely it's the mean value. So of course we can make use of that. And that's the expected value problem. Now, playing around with these expectations and the corresponding notion on when we need to take which particular decision, we can also use another model, and in fact we've seen that before, is the so-called wait and see formulation. The idea being, okay, instead of deciding now before we learn about the realization of omega, we simply wait till we are given that information, and then we determine an optimal solution. And in fact, we're allowed to decide both on our first stage decision, given omega, as well as the second stage decision, y, again, given omega and given our first stage decision x. Now, in terms of the mathematics, this is the problem that we're looking at. Inside the expectation, we are solving this deterministic problem for each and every realization of omega. We find the corresponding optimal solution with corresponding optimal value, and of that we take the expectation, and that we call the wait and see value. Everything clear? You recall that we discussed that before? Okay. Few remarks are in order. First is, you might say, well, then the distribution better be finite discrete, because otherwise I can never solve all those deterministic problems corresponding to each and every realization. So even if the problem is given to us with a continuous distribution, we might discretize, maybe sample from that distribution. And again, in the software SLP IOR, that's actually a facility. You press a button, tell it how large the sample should be, and it calculates for you the vacancy solution. In fact, it could be thousands of realizations, maybe even tens of thousands, and each of them calls for solving a linear program. Now let me ask you, solving a not too large, not too small linear program with changing parameters 10,000 times. How much time does that take? Rough estimate. Seconds, minutes, hours, days, weeks. What's your estimate? Weeks? Anybody else? How are you at mathematics solving LP problems? No, not that good. Okay. Anybody else wants to give another estimate? Minutes. It's quite a difference, huh? Weeks, minutes. Days, yeah, that's okay. We could go on for a bit. No, actually it's seconds. It's very fast. And that tells us a bit about indeed the power of the software that's behind all this. Solving deterministic LP problems. There's so much theory, and it is so well, say, implemented in those algorithms, that this is very doable. It's a press of a button, you don't even have time to take a sip of your coffee, the answer is there. Very fast. Okay, so that's the good news. The bad news is that, of course, we can talk about it since we're in charge. We are the modelers and we can do anything we like inside the modeling world. But you should realize that, of course, this is not something you can do in practice. I mean, it's the whole point. We are looking at an optimization problem that's modeling a real problem where the situation is that we have to decide on X, our first stage decision, the here and now decision, before getting that further information. So it's not of much practical value. That's my point. But still, it is very interesting because it helps us in learning about everything that deals with these decision-making problems under uncertainty. So, we are looking at approximating problems, and let's agree that this is indeed of the type that we were looking for. It's easy. I just told you it solves very quickly. But the question is, do we know what we get? So like before, I'm asking the question to you, what are we getting? Do we get a lower bound for the true optimal value, that is the one of the recourse problem, or do we get an upper bound? And as usual, I'm asking for your intuition, but I wouldn't mind if you would give me a proof, suggesting that the proof is easy. What do you think we get? Who has some intuition for this question, for this answer? I'm sure most of you have, but you're afraid to say it out loud.
I would say upper bound.
Why?
Because you're smarter at the moment you make a decision.
Yeah, but we're minimizing, right?
Yeah.
So being smarter translates to a lower bound. Okay. That's one very reasonable approach. Any further ideas? Indeed, you're optimizing. So as soon as you have this information, you'll use it to find a better, that is, cheaper solution. And so it makes sense. This could be, who can give me a full proof? Let me tell you, this is correct. It is a lower bound. It always helps if you know what you need to prove, and to prove it is very easy. How can you prove that that's...
I don't know a proof, but I assume that you do it with the set of all, like the name of omega.
Mm-hmm.
And if you wait and see, then it's just one realization from all possible realizations.
Yeah.
So it's a smaller set.
Yeah.
you know, relying on the small set.
I think it goes to more or less the same argument that Kevin was proposing. But although it is correct and it helps build our intuition, it doesn't lead to an easy proof. Anybody?
If you use the optimal solution of the two-stage, then in the minimization problem for the wait and see, you have at least as much as the best solution.
Excellent. That's it. Very easy. Indeed, in both problems, we're optimizing over the same feasible set. So a solution of the recourse problem that I denote by X star is also feasible in the wait and see version for each and every realization of omega, because it's always over the same set for optimizing X and all. So it is feasible, but not necessarily optimal for each realization of omega that holds. And if I take expectations, which I should do according to the definition of that wait and see number, that relation is of course preserved, end of proof. All right, so now we know indeed it gives a lower bound. All happy? Okay. So you could say we now know that it is a lower bound. We actually proved it, and it's a proof from the book, namely very clear and easy. But still, I'm going to bother you with another proof of the same statement, namely that wait and see provides a lower bound for the two-stage problem. And the way I'll do it is by proving that wait and see is actually a so-called relaxation of the two-stage problem. Now, I do hope that the notion of a relaxation is familiar to you. Is it? Raise your hand if you've never heard about relaxations before. Who can give me a formal definition of relaxation? It's an optimization problem related to a given problem where the feasible set is enlarged and the objective is not larger. So what you get is indeed a lower bound. Yeah? So to prove that wait and see is indeed a relaxation of the two-stage problem, indeed is a proof of the fact that we get a lower bound. And I'll explain to you as we go why I'm interested in this proof. First off, let's simplify for the sake of presentation. Let's assume that we're dealing with a finite discrete distribution. Okay? In that case, as we know, the two-stage problem actually is this huge linear program. Remember, we have our first stage decision variables X, and they are all over the place. And we have for each realization a separate decision YS, which appears only in the corresponding constraint corresponding to scenario S. We've seen it many times before, right? So this is a huge problem. Why? Because in general the number of realizations, capital S, will be large. We've seen trivial examples where there were even millions of constraints and variables. Remember? So this is a bad problem because everything is connected by the first stage decisions X. They spoil everything. They're the nasty variables in this problem. If they wouldn't be there, I would be left with a problem that nicely separates according to the scenario. Because those variables YS indeed only appear at certain places and are not connected to the other scenarios. Okay? So what do you do if you have nasty variables? You apply a trick. You see, I'm going to play a different game. I'm going to introduce copies of my decision variables X, namely one corresponding to each scenario. And now the problem is again very nice because it separates according to the scenarios. So instead of this one giant LP problem, I'm looking at a indeed giant collection of small problems. And I just explained to you, solving such a collection of small problems is doable. But of course this is not fair. What I should say is, okay, you can of course write those copies, but they have to be the same. All right? And that I enforce by including that final set of constraints, saying that each copy of x, x1, x2, all the way up to x capital S, should be the same. Those constraints are important in stochastic programming, in particular in multi-stage versions of the two-stage problem, and that's why they have a name. They're called the non-anticipativity constraints. And that's a good name, because it precisely tells what they do. They indeed say, you cannot, in taking your decision X, which indeed needs to take place before you learn about that scenario, you cannot take advantage, you cannot anticipate the future. So that's what they do. The other reason it's a good name is that to become a member of the ST community, you have to be able to say this. Non-anticipativity constraint, which is not easy at all. So practice, next time I can ask you. Okay, so indeed those NAC constraints, or information constraints as they are also called, they are now the nasty part. We agree if they wouldn't be there, then the problem would separate and we would be very happy. So the idea is now that if we relax those constraints, we have this very nice problem, and it's not difficult to see that that's indeed the wait and see problem as we discussed before. So indeed it's a relaxation, namely by relaxing the non-anticipativity. Okay? Now, one way of relaxing it is just kicking them out. A bit more sensitive, a bit more reasonable is to do something else. And we'll discuss that later when we are in the context of multi-stage problem. But I thought this would be a nice way to at least introduce the notion of non-anticipativity in the familiar setting of two-stage problems. And it gives us yet another proof of what we were after. All right. Questions so far? If not, I have yet another question for you. So what we did so far is find two lower bounds for the true optimal value, meaning the optimal value of the two-stage problem. And the natural question then is, which is the better lower bound? Now mind you, the better lower bound is of course the one that's closer to the true value, so the larger lower bound. Okay? And again, I'm asking, do you have an intuition for this result, for this statement? So what is your answer, and why would that be true? So the answer is either wait and see is better than EV, or the other way around. And the third possibility is, of course, to say, well, it can go either way. Anybody has an idea? That you show me my intuition. Here it is. No intuition. So let's go to the mathematics and that should help. Okay. What I will do is try to prove that wait and see is the better lower bound. Okay? And as spelled out, here's the first attempt, which suggests that we will fail and need at least a second attempt. Okay? What I suggest is that, okay, what is wait and see? It's the average over all those optimal values for all those scenario solutions. So what I propose is, let's look at the average scenario solution. That is, the expectation over those solutions. What's the expectation of a vector? And that's the solution again. I call it x bar, and indeed it's the expectation of those x hat solutions depending on omega. And they are all solutions of such a scenario problem, and altogether they constitute the wait and see approximation. And of course, that doesn't have to be a unique solution. We do know in any linear program we might have multiple solutions than just a. Okay? So I'm constructing this solution x bar, and I claim that's a feasible solution. That is, it belongs to the deterministically given set X naught that we've been dealing with run. It's the same set for the latency problem as well as for the two-stage, as well as for the expected value problem. Why is that true?
Convex combination.
Exactly. Each and every solution X hat of omega is a feasible solution. And to take some weighted average of those feasible solutions amounts to taking a convex combination of those solutions. And since we're optimizing over this convex set X naught, we know that such a convex combination is a feasible solution. It's a member of that set. Now, this is probably not the first time that we can observe that indeed taking the expectation and taking a convex combination is very much the same thing. It just depends on our interpretation, how we call it. But it's the same thing, using non-negative weights that sum up to 1 in our operation. And here's a nice example. So indeed, we are looking at a feasible solution X bar, and then the next step would be, okay, if I can prove that G of X EV, so my expected value problem, is smaller than G of X bar, both evaluated with respect to the deterministically given vector mu, the mean value, that's the first step. Well, that must be true, because XEV is actually the optimal solution of this problem. Right? This is objective, it's the objective of the EV problem. So this is a no-brainer. But the next step is a bit more involved. If we now can prove that this one, appearing now here, is a lower bound for, well, indeed, the wait and see value, right, that's the definition of that wait and see value, then we're done. And again, my question to you is, can we prove this? And if so, how? What is the single word that comes to mind if you look at this question? It's actually a name. Start with a J. Jensen. We know about convexity properties of G, and the question is, okay, we have G of the expectation related to the expectation of G. That suggests that Jensen might be the solution. And then we will be done. But we're still on our first attempt, so we're going to fail. And here's why. Indeed, it is very natural to think of Jensen, but now we should be precise. What do we know about G? Oh, sorry, I should show you the middle. What we know about G is the following. For each fixed X, it's convex in omega, and the other way around. For each fixed omega, it's convex in X. But what we need here is joint convexity, jointly in X and omega at the same time, so to speak. And now we simply look at what we know is the valid formulation of our value function V, namely as the pointwise maximum. We recognize those vertices of that two feasible set, the lambda k. And our expression for the vector of deviations is plugged in here. And now we see that here we have T of omega, so something depending linearly on omega, times X. That's a bilinear expression. So our function G, rather than being a convex function in X and omega jointly, is a bilinear expression, which is non-convex. So this spoils it. Although we were so proud of our knowledge of the function G and thought we could apply it here, it doesn't fly. So how can we save at least some result and obtain some result? We pinpointed exactly where the issue is. It's right here. I underlined it. If that's what's bothering you, what could you do to make everything all right again? Make stronger assumptions. In this case, it is to assume that the randomness is actually only in the right-hand side. That is, the matrix is deterministic. Because then, it's still up there, that issue disappears, because d of omega no longer depends on omega, so we do not have this bilinear form and everything is nice again. And then we have joint convexity in x of omega as required. So, the bottom line is, under that additional assumption, we use convexity of x and we can apply Jensen, and we find indeed that under that assumption, wait and see is the better lower bound. So a reasonable question would be, what if this is not the case? Then the answer is we simply don't know. It can go either way. In some applications you'll find that wait and see is a better lower bound. In some applications it's the other way around, it's the expected value problem, giving the better bound. But at least in this special case we know what we're looking at. Okay. Questions? Let's summarize what we have found so far. Indeed, we know that under our Groningen assumption of fixed recourse, EV is lower bound for the true two-stage optimal value, whereas its expected result of that EV solution is an upper bound. Also, we have this alternative lower bound which holds always. And we just argued that under the additional assumption that T is fixed, then actually we have that wait and see is the better lower bound. EV is lower bound for wait and see, if you will. And what we now will do is look at the two gaps that we're dealing with, namely the difference between the true value, so the optimal solution value of the recourse problem, the difficult recourse problem, and its upper bound. And then we'll also look at the other side, namely the difference between that true optimal value and the wait and see lower bound. And we'll see that there's actually something to say about it, more than just it's a number. Okay, first we look at the difference of TS with its upper bound EEV. And okay, here's the context. That they're representing two approaches to the same problem, right? TS, the recourse problem, the two-stage recourse problem, is its solution X star, which indeed uses as the criterion the expectation of G. Whereas the EEV takes a different solution, which is obtained in a very different way. It's a solution of a deterministic problem. Now, instead of talking about deterministic and stochastic, it's much more convincing to say that X star, coming from the two-stage problem, is a solution to the true problem formulation. Because that's what we feel. Randomness is actually an important part of that given problem, so we should do justice to it by properly modeling it. That's why I call that the true or sophisticated model. Whereas XEV comes from that four-man solution approach, the expected value problem, which I sometimes call the naive modeling approach, or the simplified model. Every not so nice word that you can think of. So, from that perspective, it's very reasonable to say, okay, the difference between the two, the evaluation of that four-man solution XEV compared to the true objective value, that we call the value of the stochastic solution. That's what we gain by using a proper model, sophisticated. This is the name under which it's known in the literature, the value of the stochastic solution. Mind you, of course, that's non-negative by definition. still, of course, it could be that instead of looking at a minimization problem, you're looking at a maximization problem. And then the sign of that difference, EV, then becomes a lower bound in such a maximization setting. Then the sign, naively approach, would become negative. But that cannot be true, of course, because we're talking about different values of the stochastic solution. So if you're looking at a maximization problem, please also use this notion to mean something that's always non-negative. What is the interpretation? As I already remarked, is what we gain by all our efforts going through this modeling and solution approach for the true model instead of using the naive model. So that's the value of the stochastic solution. A few remarks, and then we'll have a break. So far, when we introduced those different modeling perspectives, we always found numbers giving bounds that were obtained without solving that difficult problem. Here, the situation is different. To be able to talk about that value of the stochastic solution, you have to solve the recourse problem. So this is, in a sense, knowledge after the fact. You learn something about a difficult problem, and it is interesting to know, but you only get it after solving the problem. The second remark is, and it's more or less the same as I made before, also here we're talking about a get, so a number, difference between two values, and we can look at the number and make statements about whether this is small, large, and so on. And again, it's important to consider this from the various perspectives. Absolute numbers are interesting. If it's millions, it's probably interesting. Millions of euros it is. But also relative numbers. Depending on the application, already a very small percentage can be highly relevant. So at least take those two perspectives and make sure that in any application you discuss the value of the stochastic solution. Okay, I think this is a good moment to have a break, unless there are pressing questions. If not, we meet at 3 o'clock. Oh, something to ponder for you during the break. If you may remember that after this lecture there is the master seminar. Highly recommended. I don't know actually which room it is. Does anybody know? So in the same building.